Well, this is your host, Thomas O'Neill, and we're talking about the Riemann conjecture or hypothesis. And I'd like to tell you exactly what I did. And we're looking at the Riemann zeta function. And if you'll notice right over here with the infinity, and I substituted the square of the gamma. And what the gamma is the result of finding the the number uh, between the goalposts, and more on that. Um, how you do that is you verify using the gram points of the Riemann-Ziegler theta function. And if I can be more um, efficient with what I'm discussing here, 14.1347 is the first gamma, and that's the 0. And between the goalposts of 14.1 and 14.2 is 14.1347. 14.1347, which is the first gamma known. And if we go into here, this is the infinity symbol that I edited. And here is the equation that I built with Claude. Now, here's 14, and if you square that number, so put in 14, there's a residual that's consistent, and this is a pattern I found using the formula of the Riemann function. So we'll just use the default, and here it is. There's the square of 14. 14 is the gamma. So it finds the gamma. It's correct with the 196 is the square, and there's the residual. And this is what I want to get into, is the residual. And you will find this is a pattern that the residual is something that I found with gammas, and this is consistent in all squared numbers of the gamma, the first part of the gamma, not the whole gamma number. And this is a true 0. Now we can take, let's take 21. And here we go again. 441 is the squared number, and the gamma is 21, 0, 220, 0396388. And the gamma, once again, the residual is 0.99933. Let's say we wanted to put in 22 just to see what it says, and we'll use the default. Default band is between 0.9 and 1.01. So we'll put that in. That's the default. And if you notice, 484 is the square of 22, but this is saying wrong gamma because it's not giving you the true gamma. And the residual is 1.04, so that's out of the bounds. Now let me read you something, what I found with, I had Claude do a write-up, and let me read it to you. The squared index residual pattern is real, exact, and explainable for a non-trivial zero at height gamma. Truncating the zeta series at n equals gamma squared, and measuring the magnitude at the zero yields a residual that tends to 1 because that residual is the magnitude of the discarded tail, and the squaring rule makes the tail integral equal gamma squared 1/4 plus gamma squared, which approaches 1. The pattern is a genuine consequence of the series structure and the exponent 1/2. It is selective enough to act as a necessary signature of a zero, and it tightens predictability for higher zeros. It tightens predictability for higher zeros. It is not a proof about the location of zeros off the critical line. Because it's measured only on the line, its value is pedagogical, and diagnostic. It gives a clean, computable relationship between a zero's height and natural truncation of the defining series, and it illustrates concretely how the tail of a divergent on the line series still carries exact structural information through analytical continuation. So there you have it. And so I can show you these are finding Graham's points, which is which relates to this. These are Graham's points right here, the goalposts, which is the gamma, which is in between the goalposts. So, so, so thank you.